Okay, so what is thermodynamics? Thermodynamics is the study of how energy transfers from one form to another. And that could be a form that involves a physical process, a physical change, or a chemical reaction, chemical change. And we often think about the heat that's involved in the reaction. We think about work that can be done. Okay, so those are in chapter 5, and we're looking at, in that case, enthalpy. And we've seen a little bit of that when we were talking about making solutions. Okay. A recall for you. The first law of thermodynamics, essentially, the short version is that it says energy is conserved. Okay, and so what does that really mean? It means that energy can be transferred between reactants or between materials, but the total quantity of energy remains constant. Okay. So for chemical reactions, we're thinking about how they may give off heat or absorb heat, whether they're an exothermic or an endothermic reaction. It can absorb from the surroundings or essentially give off heat to the surroundings. So one of the things that we're going to need to be thinking about is system versus surroundings, okay, when we're thinking about some thermodynamics here. The other thing we've talked about is that a reaction can perform work, okay? So the example that's shown here is we have zinc solid reacting with 2 hydrochloric acid. This reacts to form zinc chloride and hydrogen gas. Okay. And so if we perform this reaction in a closed vessel with a piston on top, the reaction proceeds. It also gives off heat. We can add heat as a product. Okay. So it's an exothermic reaction. And as that hydrogen gas is produced, because gases expand, it has the ability to lift that piston. So now we can get that reaction to perform work for us. So this reaction performs work, moves a piston, and it also produces heat. Okay. So enthalpy is the heat that's involved in a chemical reaction. And you may recall seeing the equation Q equals delta H, where delta H is the change in enthalpy for a reaction or a process. Okay. If we have a chemical reaction and we want to determine the heat that's either given off or used up during that process, we can calculate the enthalpy if we know the enthalpy for the individual products and the reactants. So the enthalpy for a reaction, or delta H for the reaction, is equal to the sum of the moles times the delta H of formation for the products minus the sum times the moles, or sum of the moles times the delta H of formation of the reactants. Okay, this is your sort of 1210 first semester Gen Chem enthalpy reaction, or enthalpy equation for determining the enthalpy for a chemical reaction. So the delta H's of formation for chemical species, you can find these in a table, delta H of formations. And so the units are usually in kilojoules per mole. Okay. So we can calculate the heat given off or used up during a reaction using this formula. Okay. So for the reaction of methane plus chlorine gas forming carbon tetrachloride and hydrogen chloride gas, we would need to look up the delta H's for each of those individual species and then use this equation. So let's go ahead and calculate that. So first for the products, we're going to have, let's do it this way. We have 1 mole of carbon tetrachloride. Its delta H of formation is minus 135.4 kilojoules per mole. We need to add to that 4 times that for the HCl, so the 4 from the stoichiometry, minus 92.3 from the table. Okay, all of that gets summed up. Then we subtract, I'm going to need to scroll over here, 1 for the methane, stoichiometric coefficient of 1, times minus 74.9 kilojoules per mole, plus 4 times 0 for the chlorine gas. And then when we solve for this, we'll get delta H for the reaction is minus 429.7 kilojoules. And you'll notice this is given in kilojoules, not kilojoules per mole, because we've multiplied by moles in our formula here. So these are the 1, the 4, those are all moles. Yeah. Maybe. CO4 minus Cl2 should be 0. So products minus reactants? Okay. Okay. Delta H is negative. Is this exothermic or endothermic? Exothermic. Okay, cool. Y'all remember doing this kind of thing at some point in your lives? Okay. We are going to do some similar using entropy and Gibbs free energy. So that's why I wanted you to see that. But more specifically for this chapter, we are going to be thinking about whether a reaction is spontaneous. So what does that mean? So a spontaneous process is a chemical or physical change that occurs without any outside help or any input from anywhere else. And the reverse of a spontaneous process is a non-spontaneous process. So make sure you can use spontaneous and non-spontaneous. But whether a reaction is spontaneous doesn't tell us about how fast a reaction takes place. It just tells us if it goes in a certain direction. Okay? So for instance, diamonds naturally, spontaneously go from diamond, which has a nice crystal structure like this, to graphite, which we value much less than diamonds, right? And so your was this Kay Jewelers diamond is forever? Not exactly true. I mean, in terms of geologic time, perhaps within a lifetime, yes. But so this is a spontaneous process, going from diamond to graphite. Okay. All right. It's just incredibly slow. So determining whether a reaction will occur is essentially the same as determining if a reaction is spontaneous. Okay? So will the reaction occur in the direction that's written is the same thing as saying, is the reaction spontaneous? If a reaction is spontaneous in the forward direction, it's going to be non-spontaneous in the reverse direction, okay? And vice versa. Unfortunately, enthalpy, or the heat given off in the reaction, doesn't tell us about whether a reaction is spontaneous. We need the second law of thermodynamics, which is talks to us or tells us about entropy. So the second law of thermodynamics states that the total entropy of a system and its surroundings always increases for a spontaneous reaction. Total entropy of a system and its surroundings always increases for a spontaneous reaction. Well, what is entropy? Okay, so entropy is a measure of how dispersed the entropy or the energy in a system is. And so sometimes we think about entropy as a measure of disorder, and that's a good way of thinking about it. Okay, but we're going to think about it slightly differently here when we're thinking about where the energy could be in a system and its surroundings. If the system that has energy dispersed in many ways, if we compare that to a system that does not have energy dispersed in many ways, we're thinking about a system that has greater entropy if it's got energy in lots of different areas. Okay, so if we're thinking about a hot cup of coffee, all right? So we know that a hot cup of coffee is going to spontaneously cool, okay? And it never spontaneously heats up, okay? So the forward reaction, the spontaneous reaction is going from hot to cold. The energy that gets dispersed when coffee is cooling, you've experienced this. You get steam, the cup that's holding the coffee gets warm. Maybe it's on a saucer if we're real fancy, and then that saucer gets a little bit warm, okay? The energy becomes dispersed. The entropy increases. There are lots of spontaneous processes. Okay, we talked about the middle one here, heat flowing from hot to cold. Another really easy one to imagine is the rusting of iron, or oxidation. So you put iron outside in the rain, it's going to rust very quickly. You can also think about a rock rolling down a hill. That's a physical process that is a spontaneous process. I used to have a joke in here about spontaneous human combustion. Didn't play well last time, but I enjoyed it. I didn't put it in here this time. Imagine spontaneous human combustion joke. Right there. Okay. Okay, so this is really getting into how physical chemists think about entropy. Okay. It is a measure of molecular randomness. Okay. In using the definition that it's a measure of disorder is also an acceptable way of thinking about it. Although a physical chemist would yell at you and disagree. I don't care. The entropy, okay, we're thinking about the arrangements available to a system, and we also need to think about microstates. So what's a microstate? So a microstate is one possible arrangement for a given system. So let's think about this in terms of like one of the more simple ways of how this could happen. So let's say we have this a 2-bulbed flask, okay? And we have 4 different atoms, A, B, C, and D. And we put 4 atoms into this 2-bulb flask. If A, B, C, and D all stay on the left side, that is one possible arrangement. And it has 1 microstate, okay? That's the only way of thinking about how that exists, right? Stay with me, okay? If we then let one of the atoms go into the right bulb, but the other 3 stay on the left bulb, we have 4 possible arrangements. These are 4 microstates. So we could have molecule A on the right, or molecule B, or molecule C, or molecule D. Those are all the same type of arrangement, but there's 4 different microstates possible. Okay? The third arrangement is we have 2 atoms and 2 atoms. And now there's 6 possible arrangements for this to happen, or 6 possible microstates for this to happen. And that is the most probable way of finding those atoms in real life if we were able to actually do this, because it has the highest number of microstates. So the most number of microstates is the most probable to occur. And you can see the other 2 options here. We've just sort of reversed what was in 1 and 2. Okay. This sort of idea to phase changes. If we think about the possible ways in which the molecules of water can arrange themselves in the solid ice form, okay, those molecules are going to be held pretty tightly, pretty rigidly in some sort of crystal structure. As we increase the heat, the entropy increases. Those molecules start moving a little bit. Eventually, they start sliding past one another. Now they've got more positions that it's available to them. And we get into the liquid phase, okay? And the number of possible microstates has increased greatly. So we've increased the entropy going from the solid phase to the liquid phase. Even more so, we increase the entropy when going from the liquid phase to the gas phase. When water is in its liquid phase, it's sort of bound by wherever the volume of water is. But once it goes into the gas phase, and if it's not in a closed container, it can go anywhere, okay? So we've really drastically increased the entropy. So what we see is that within a phase, the entropy increases gradually as the temperature is increased. So in this plot, we have temperature on our x-axis and entropy on the y-axis. You can see for a solid that as we increase the temperature, the entropy does increase. Adding heat allows those molecules to vibrate a little bit more. Eventually, there's a phase change, and we see a huge jump in the entropy with just a small change in temperature. Within the liquid phase, again, slow rise in entropy. Going to the gas phase, huge jump. And then within the gas phase, we're even able to increase the entropy as we apply more heat to the molecules in the gas phase. Okay? All right. Questions on any of this? All right, we will continue thermodynamics on Friday.